for joining us here on DeadCat LiveCat for this interview with Pedro Lopes. DeadCat LiveCat is an online quantum computing magazine founded by law firms BLG in Canada, Marks & Clerk in UK, and Zuber Lawler in US. We're attorneys, but we're also scientists, engineers, and futurists focused on the likelihood that quantum computing and AI are going to change the world. My name is Tina Decker. I'm an intellectual property lawyer at Ford & Liner Gervais, which is a law firm with offices across Canada. Today, we have Pedro Lopes joining us. Pedro is QuEra Computing's quantum advocate. With a PhD in theoretical physics, his research career through Brazil, USA, and Canada explored topics in quantum matter and topological physics. He's passionate about communicating quantum computing at all levels, developing public-private partnerships, and helping users and developers alike understand ideal entry points in quantum technology. Welcome, Pedro.
Thanks for having me, Tina. Good to see you.
Good to see you too. So to start off, how did your journey in quantum research start, and how did you get to where you are today?
Non-linear path, right?
Yeah.
Quantum is linear, but my path is non-linear, I guess. It's so I did my PhD in Brazil. Part of it, I was in the USA, in Midwest, South Illinois. And as you're just mentioning, my background is in quantum matter, not quantum computing proper. Although my supervisor in Brazil, his background is actually very closely related to quantum computing. So one of the first things that I learned in my career was about methods for quantum dissipation and these methodologies that are pretty much behind how people evaluate how qubits perform. If you hear about these buzzwords of fidelity, etc., and decoherence, that's exactly what his work was very much involved in. But I decided to tread a different path and worked on topological physics and materials and the creation of what we call fractionalized quasi-particles, which means like a fancy word for having some collective behavior where like a puddle of electrons look like half an electron in some sense.
Okay.
It's kind of a funny thing. And that ended up bringing me into quantum computing for a different reason. It's because those fractionalized quasi-particles, they quite often are very good candidates for qubits. They're protected from the environment, et cetera, et cetera. So you hear some of that. And I ended up here at QuEra after deciding to tread a slightly different career for a scientist. I wanted to really at some point start supporting the environment and the ecosystem that allows science to happen. I think that there is a lot of scientists that, doing science is a privilege, but there's a lot that has to happen behind for this to work. Quite often people that are doing science, they are deeply enthralled with the process of doing science, and they don't necessarily want to deal with the navigating the politics and everything else.
Yeah.
And that's what I wanted to do. I joined QuEra January 2 years ago, and first in a business development role, and that business development evolved into this quantum advocate role.
Okay, that's very interesting. And so, yeah, I guess moving on to the next question in terms of being a quantum advocate, I mean, what does that mean? I'm a lawyer, so I have a certain understanding of what advocacy means, but I think a quantum advocate in quantum industry, that probably means something else. Can you talk about that?
Yeah, that's fair. I don't think that the only laws I deal with are the laws of physics, but
yeah.
The role is related very much to it certainly stems from business development. It's let's say a more tech-oriented path inside the business development. Some places call it quantum, or tech evangelism. I don't always like to use the term. There is no Christianity here on this role. So sometimes I call it proselytism, but then people don't like the word either. But the bottom line of this story is that as a acquaintance of mine in the industry says, evangelism means to be the bringer of good news. So quantum evangelism or quantum advocacy here means to bring the good news. So to get people involved in the tech, get people understanding how to operate this, what are the good points of entry, why to get involved with it, when to not get involved with it, and how to do all of this in a way that is productive for themselves and for everyone. I also run partnerships and government relations and a whole education program for both the users and executives.
Okay, that's really interesting. And I guess one question I'd have is, I mean, if we're bringing the good news about quantum, you kind of touched on this, there's sometimes maybe bad news with quantum. How do you, I guess, in your role as a quantum advocate, how do you combat sort of the hype that we're seeing in quantum? I'm sure there's well, I'll let you speak to it. We know there's a big hype problem in quantum right now, and what does that look like for you in your role?
I would be very curious to hear also at some point about the legal aspects of this, right, and how you guys deal with that. But on our end, so hype, there's many facets to it, right? It's a spherically complicated problem, meaning that it's equally complicated. It doesn't matter which angle you look from. From the perspective of investors, I have even heard people saying that there's not enough hype, that the amount of VCs pay attention to quantum in comparison with what happens in the rest of the range and spectrum of possibilities to what invest on. Quantum is very small. It's really growing, and there has the hype that exists. They consider it's not damaging for venture capitalists. I'm not going to say that I agree or disagree. This is something that I heard and I found an interesting aspect. For us, I think that the key aspects are to get people excited while keeping them realistic about what are the prospects, where we are right now. So the bad news, let's say, on quantum is always that it's not as fast as we would like it to be.
Yeah.
But we are, humans are a very demanding species, and the reality is that there has been tremendous amount of progress in the past 5 years that I've been closer to this. 10 years since quantum computers started to reach the hands of people everywhere, and 30 to 40 years since it was conceptualized, right? But I think that being on point with our technical aspects while finding a language that enables people to relate and to understand and to compare with what they are perhaps more used to. That's perhaps what the approach that I try to take and that QuEra tries to promote, right? Excitement, right, while staying within the realms of what's precise and what's realistic.
Yeah, for sure. So what does that look like in terms of, bringing that excitement to people that you want to bring into quantum tech? And also, I mean, you touched briefly on investors as well. So how do you sort of convince them that, quantum is worth something?
Right. The investor conversation is not for me. I don't really
Fair enough.
With investors myself. But I do deal a lot with both government agencies and with academics and with companies themselves as well, like private industry.
Right.
And there are many interesting directions in there. Like from government, the conversation is always about why should you or how do you justify investing taxpayer money on a topic like this, right? And it's very interesting when you notice the size and the complex dynamics that exist between countries like North America, countries in Europe, and East Asia within the quantum space. There's like a fierce competition. At the same time, there is like a spirit of collaboration, and at that point, I think that the way that I usually go about this is really conveying to people how quantum tech is really an opportunity for economic development for these countries. I think that they create strategies, right? They have global strategies. And those global strategies, they trickle down all the way to local governments, states, provinces, then cities, and then the organizations inside. And this ends up as being a great opportunity to create career paths for new groups of people. Like it's not every day that you see a budding industry, right? Starting from the scratch. And being able to do that in a way that is modern, is aligned with our current values, I think this is a great opportunity to bring more equality, more diversity, create opportunity for everyone, and help develop perhaps regions in a province or states that are less developed. So instead of investing in a place that is already developed, you seek for mechanisms to leverage this industry to help grow a different area. For companies, the conversation is slightly different, right? Because you are always fighting the conversation of, okay, is there an ROI, a return of investment on what you're doing or not, right? Are we at production level, are we not? And I think that we are in a very much experimental stage, and trying to kind of connect and bridge applications and the technology. And what I see for companies is that this is very much a great time to also kind of renew their mindset and the way that they approach their employees and their pursuit for innovation, right? So quantum technologies require long-term investment, long-term attention to a technology and to your needs. And I think it's a very, very important learning experience for companies that either are budding and therefore they have to innovate because innovation is what they do, or for large companies that have by now, I expect, experienced more than once, right? If you have a company for 50, 60, 70 years old, you have probably figured out that innovation is very much part of staying alive, and as humans and our relations change, I think that how you create innovation and foster innovation inside your company also changes. And I think that this is a great opportunity for that.
It's interesting that there's so much opportunity in innovation and opportunity in quantum computing, as we expect as well. But I feel like we're seeing a lot of, I guess maybe because, like you said, it's experimental, it's in its nascency, but there's a lot of hesitancy or even just unknown or uncertainty about how companies can use quantum computing in their industry and in their field. I think it'll be really interesting to see how that sort of shifts into like companies taking that innovation mindset of like, no, we need quantum computing, kind of like what we're seeing with AI, right? Like we see a lot of companies where it's like, no, we have to use AI now. And I wonder if we're going to see a similar transition with the quantum. We'll see.
Well, it's I would say that this question is priceless, but these days this question price it's $5 million in the X prize, right?
Yeah.
To put that out exactly to promote more innovation and clear directions of how to apply quantum computing. So definitely very curious to see how this will evolve.
Yeah, for sure. Okay. Well, let's talk about QuEra. So QuEra is a Boston-based company, and my understanding is you build neutral atom-based quantum processors. So can you tell our listeners more about QuEra's technology?
Absolutely. So when we talk about neutral atoms, that's a little bit of a mouthful to just say atoms. Atoms are the kind of I wouldn't say the most basic, but they're generally basic constituents of matter. Chemists deal with them all the time. We have a whole periodic table of them to play with, right? And these building blocks, and we call them neutral because an atom is usually composed by a nucleus, like a center part, and an electronic cloud. So it has electrons. The electrons, they are charged. The nucleus is also charged. They bind together. Opposite charges attract each other. So they bind and they bind until exactly they become neutral, right? Exactly when amount of positive charge is exactly equal to the amount of negative charge. Now, there are other technologies in quantum computing that use atoms that have charges removed from them. Right? So when you remove a charge from an atom, we call that an ion. But to make extra precaution, extra efforts to make sure people are not confusing things. We don't call them just atoms. We call them neutral atoms to make sure that people remember that these are not ions. And ions, because they are charged, they are kind of easy to manipulate around, because you can make electric fields and repel and attract them, and they repel and attract each other. So there's a thing about ions that they always see each other. They're always interacting. Whenever you put them more or less close, they're always seeing each other. And that is a double-edged sword, because it's great because it's easy to manipulate and hold them in place. And on the other hand, they are always interacting and they are always actively engaged with each other. So isolating them can be quite tricky. And also positioning them in ways that are not linear, one-dimensional, is very difficult. Neutral atoms is a different story, right? These guys are neutral. You can pack them together. They don't see each other. They do not complain. You can do whatever you want, but it's hard to hold them in place. And the way that we figured out to hold them in place, there's a couple ways, but the most let's say, famous right now is to use what we call laser tweezers. So a laser tweezer is just a laser beam. And as I like to say, laser beam is not like lightsaber, right? Lightsaber, you watch Star Wars, lightsaber is straight. Laser beam is not straight. Laser beam has a little waist. And this waist is what sometimes you hear called as a focal point. And the focal point happens to be sticky, so you can hold things with it. If you shine it through something that is smaller than it, you can hold it in place. Some biologists use it to hold cells, and we use it to hold atoms. In our case, rubidium atoms. Rubidium lies in the first column of the periodic table, which, for the anger of all my chemist friends, I would say if it's in the first column, it's hydrogen. Okay, it looks like hydrogen. Hydrogen. There's one electron to play with. It's heavier, and technically the energy structure is more complicated, but it feels like hydrogen.
Okay, is rubidium selected for any reason also for like how you're able to isolate it compared to other atoms, or how do you go about isolating single atoms of rubidium?
Yeah. So there are a few different choices. So in the first column, the mostly used atoms are rubidium and cesium. And sometimes there's a group at U of Chicago. They use the rubidium and the cesium in the same processor. So they create a processor with dual species, as we call it. There are other groups, let's say in California and Colorado, also in Princeton, that have been playing a lot with metals and like ytterbium and strontium. And these are more complicated. You have like two electrons to play with. It's in the valence shell. The structure is much more complicated, but there are other advantages. And each of these atoms, there's no single, this is the best. So some are better because of this, some are better because of that. Some lasers are easier to develop for one atom type, or other lasers are easier to, because the whole problem, the whole difficulty as far as engineering goes, is to get lasers with a lot of power, but ultra clean, very, very high stability of noise and etc. So the way we go about rubidium, we cannot take anything much lighter than that because it's hard to hold in place. It flies.
Okay.
Right. And anything heavier than rubidium or cesium starts to get kind of complicated for other reasons, like radioactivity or things like that. I don't know.
Yeah. I'm just thinking of other applications I've heard of, like cesium being used for and stuff. And
not all cesium is radioactive. For us, we use rubidium 87, as we call it.
Yeah.
So what happens is you heat up a little element of rubidium with a current that emits a gas, and then you cool down that gas. You don't cool down with ice or with refrigerators. You cool it down by holding it in place with what we call a MOT, a magneto-optical trap. Is a trap with magnetic fields and optics and light, magneto-optical, that cools this cloud down with a few hundreds of thousands of atoms. And then you shine those lasers through that cloud. And because the atoms are slow, they get caught in the laser. And then you have your processor.
So you're taking your laser tweezers and just picking out your
one
atoms.
by one.
One by one. Okay.
One by one.
And I guess you kind of touched on this, because my question was going to be, can you combine different types of atoms? But it sounds like you're tuning the laser for the specific atom. And so you're sticking with one atom per, I guess, like
Yeah.
array or processor.
So as far as I can tell, for holding atoms in place, it's possible to use the same lasers for more than one species. When you're starting to operate the qubit, and the qubit here, right? So the basic element of computation for the computer, this is going to be the energy levels of excitation of this atom.
Okay.
So that requires very, very specific lasers that are dependent definitely on what's the atom that you're using. But holding it in place, there's a couple ways. Some atoms you prefer to trap on the high intensity of the beam. Other times you make beams look like a donut. It's not really a donut. It's more like a straw, right, with a hole in the center. And then it prefers to be trapped in that little hole.
Okay.
And other ways, sometimes people create kind of standing waves. It looks like an egg carton, and then you put your atoms in the where you would put the egg of the egg carton. Yeah.
Okay, that's very interesting. I love all the analogies. It's fun to picture my eggs, but they're atoms in my egg carton. Anyway, so let's take those concepts now. Can you explain a bit more how we go from, you have your neutral atoms, and how does that turn into computations in a quantum processor? Can you sort of tell us the story there, especially for our non-technical listeners, how do we get from atom to computer?
Right. So the way I like to explain quantum computing itself is always to remember people that it's not about going from computation is going from point A to point B, right? So point A is where you are, you have some data. Point B is where you want to be, right? Which is going to be the answer of a question. So you have to manipulate the data on point A and until it becomes the data on point B, which is the answer to your question. And the way you manipulate is going to be your logic. And a quantum computer doesn't go from point A to point B faster. It's not like driving fast. It's more about changing the road, right? So the rules are different, right? It's like driving in Canada or driving in UK, right? It depends on the side of the road you're driving. Like one of them is allowed, the other is not. And the conversation here then goes by being able to manipulate information in a way that is controlled by quantum mechanics. So these atoms, the apparatus is very warm, it's room temperature, but the atoms, because you hold them in place, so absence of movement is cooling down. And these guys, they are going to be down at microkelvin range, which is pretty much like 1,000 times colder than you would have, for example, a superconducting qubit.
Right.
So these guys are there and they behave quantum mechanically. And now it's a matter of using lasers, other lasers, to excite these atoms. So to deposit energy inside and remove energy from it. And whenever you deposit energy inside of the atoms, they can puff up. They can get bigger, right? So one thing that is interesting about neutral atoms, as we operate them, there's a couple ways of operating. We call them analog or digital. Analog is kind of a system where you just control the spontaneous energetics of the system to do a calculation. Digital is this gate-based that looks like quantum or classical logic, looks more like a logical computer. And in the case of gate-based, what we do is we don't operate qubits. We operate 3 energy levels, 3 states of information. 2 of them that are super protected. They are like completely disconnected from the environment. We call them hyperfine states. So some interaction with the nucleus of the atom allow for that. And then there's this third state that I say up here because I'm pointing with my finger. But if you're just listening, you're not seeing my finger. But just imagine that there's 2 guys that are 2 energy levels that are low and one that is much higher. This much higher, we call it a Rydberg state. An atom that is put in a Rydberg state is really puffs up. And so unless I tell it to puff up, it does not see anyone else. It will only see people when I tell it to puff up, when I deposit enough energy. And when it does, it can start to generate some conditional logic in the sense of if I have another atom close to it, one is puffed up, the other atom that's close to it cannot puff up at the same time. And that's when they start to see each other, and that's when I start to entangle them and that's it. There are a lot of again advantages and disadvantages to each technology.
Okay, I guess that would be my next question. We've learned a little bit more about the neutral atom tech from you, and you were kind of implying there's also the ion trap based processors, and you told us a bit of the differences between ions and neutral atoms. But I guess the big famous one is the superconducting qubit. So that's the one I'm curious about, but maybe there's others you want to talk about as well. But what are the advantages of the neutral atom processors over the other qubit implementations? And my next question would be, what are the disadvantages as well?
We can definitely cover both of them. So as far as advantages go, I think that there is, we all hear, if you're for 5 minutes in the industry, you will hear somebody talk about the S word, right? Scaling, right? So what happens to scale? Like you need more qubits, you need more atoms or qubits, and you need to make these computers larger and more stable and more coherent. And one thing that is typically underappreciated when talking about scaling is the controls problem. But what do I mean, right? So if you are very angry with your laptop and decide to break it open and look inside, I don't recommend it. You can pull up with your processor and you see, well, you will not see actually, right? There's just so many transistors there and pretty much the bits that you really cannot see with our naked eye. And usually you don't have like you really literally have like billions of these elements in your processor, and you don't see billions of cables in your laptop, and you don't see billions of cables on your keyboard, by the way, billions of keys on the keyboard.
Yeah.
Usually the access to the processor bits is usually on the border of the system. So you typically have a ratio of 1,000. So it's millions of control lines to billions of bits. And that's pretty good. You don't want to control so many kind of voltage and electronic signals. Now, if you look at a superconducting quantum computer today, what you see is that you have 3 cables for every qubit, right? So I was talking about 1 billion bits to 1 million cables, and I just reversed it, right? So this would mean 1,000 bits for 1 cable, and I'm saying 3 cables for 1 qubit, right? So it's a factor of 3,000 difference.
Yeah.
And this is very problematic, right? These cables, they are expensive. They cost thousands of dollars. If you want to make a computer with 1 million qubits, that's pretty much going to cost billions of dollars for 1 computer. And so you cannot simply scale superconducting qubits as they are now. I'm not saying that there are no alternatives. People talk about things like cryo-CMOS and things like that. I don't want to go in details, particularly because I don't know how they work in that much detail. But that's the problem for scaling is controls, right? And what we have with neutral atoms is exactly a capacity to, because these atoms, they are living in free space. And we have something called AOD. We like our TLAs, or 3-letter acronyms. So the AOD is an acousto-optical deflector. It deflects optics light via acoustic signals. So pretty much this allows you to take a bunch of laser light, and now I'm making with my hands again, but if you're just listening, you have to imagine that you have a lot of like 10 laser beams, and with a little acoustic signal, you can move all these beams together and make them move together. So this means that with a single signal, I can move tens of qubits. And right now, that's exactly the key advantage of this technology, is this ability to, with few laser beams, 5 to 10 voltage channels and 5 to 10 laser beams, control 300 or 400 atoms in a single system. So this is greatly simplified. The fact that our atoms only see each other when we want them to see each other is another different thing, right? So ions, as I said, they're always seeing each other. So decoupling qubits from one another can be difficult. So that's how I compare those technologies and what's the key advantage. Also, in atoms, we can aim at 2-dimensional systems that allows us to get more qubits. There are approaches for that with ions as well. I'm not going to be unfair with it. What's the difficulty with atoms? The key challenge that people say is speed. So they're a little bit of slowpokes. They can be like really like 100 to 1,000 times slower than a superconducting system. But I think that the expectation is that within a few years, definitely less than 5 is the expectation, we are going to be operating neutral atom quantum computers with order 10,000 or more atoms and order 100 logical qubits. We can get to that in a bit if we have time. But the point is that let's get there first, because when we do that, I mean, I think that many people in the industry have heard of this kind of quantum supremacy type of experiments that always end up not being exactly quantum supremacy, but doing calculations that are beyond the classical computers is going to become a quotidian experience. It's going to become an everyday thing. And when that happens, when every day we're doing calculations that are beyond the classical computers, our conversation is going to be completely different. I don't think that anyone in the industry knows what's going to happen when we do that. And I'm pretty convinced that neutral atoms are going to be able to do that first. Then we start to worry about speeding up. I think that that's
Right.
what we're having right now.
Yeah, it's interesting because I mean, I think it's been pretty, I mean, you can correct me if I'm wrong, but I feel like it's been well accepted that for a long time now that it's not just about the qubit number, right? But still there's a lot of articles that we see that are saying, such and such company reaches this goal, that goal. And it's always about the qubit number, but you've kind of shed some light for our viewers that there's a lot more. I mean, like there's the speed, the fidelity, decoupling, all of these different things that we have to consider. And, I think the different technologies are better in some places, worse in others. And
yeah, the volume of the machines themselves. I mean,
yeah.
If it's going to take a whole block in New York to create a quantum computer that is scalable, we're not going to have many of those on planet Earth. So that's going to be
That's
hard.
where our normal computers, like our classical computers, started, though. They used to take up an entire room, I guess would be the argument.
Yeah, well, I think that the problem is that we are looking in a different direction, right? We are looking at, to be able to do calculations, we would need to grow them. It's
right.
And we need to make sure that it's not just a matter of size, but how many of those can we make, right? Otherwise, this will not get into the hands of as many people, and then they won't be as useful.
Yeah. Well, that segues well into the next question, which is, what are some use cases for quantum computers that we can realize now? And if it's helpful, maybe specific use cases for QuEra's processors.
Right. So that again, I emphasize, is the $5 million question. X prize, go for it.
Yeah. Yeah.
I think that there, as far as I know, no one has been able to really put a quantum computer in production for anything, for doing any calculation, really faster in any way than a classical computer would be able to do. But faster is not the only thing, right? Sometimes it's easier to deploy. Sometimes it simply takes less expertise to generate a solution. Sometimes it's less energy. Sometimes it's more accuracy. And the whole industry is trying to navigate finding exactly those. And there is a strong feeling that we will not be able to unequivocally answer that question of what are the best applications until we are able to produce fault-tolerant quantum computers. We can talk about that in a moment. Given that, where do you expect to use quantum computers? Well, it's a computer. So anywhere you would need to compute problems of high numerical complexity, right? So this includes optimization. For us, I think that what we see and what literature points, there's been some interesting papers out of Caltech suggesting that the chemistry and materials space is really the place where things remain optimistic. So chemistry and materials, but of course, even within chemistry and materials, that classical systems are pretty good, and most chemical reactions are not that quantum. So there is a lot to be thought about there. There is a lot of interesting physics applications, of course. I am not how to say allergic to to physics and the needs and
Far
desire.
from it.
Far from it. But of course, I mean, there are directions within the finance industry. There are directions within biotech. Everything is very much in flow. So if I'm being, how do I say this? If I'm being unprecise, is because indeed we are in a discovery time for all of this, and I think that the machines that we have today, we really use them for simulation of quantum systems, for playing with some optimizations. Whenever you're thinking about quantum computing, you don't want to look at problems that your computers already solve well. You want to look at problems that your computers do not solve well. And there are some optimization problems that fall within that category. There are some simulation problems. We have been working very deeply on quantum machine learning methods also, so using quantum computers to deploy machine learning methods to solve classification, regression, time series extrapolation. Keep an eye, there's going to be a paper soon.
Okay, sounds good. I guess, so most of the end users then it seems to be primarily in the research community and not so much.
Don't get me wrong.
Okay.
Don't get me wrong, right? The research, there are many companies that have already identified the importance for research, right? So BMW has used our computers. There are papers out there. We have worked, there are several companies you can see on our website, but in the energy space, in the aerospace as well. We have been working with banks. So it's not that traditional industry is not using it. It's very much important, right? But those are, the question is, who are the pioneers and what kind of value they are developing for their own environment by working within the quantum space.
Yeah, that makes sense. It's exciting developments, I think. And yeah, it'll be interesting to see what comes out of that with those different collaborations.
Yeah.
So we've kind of been touching on this subject without really getting to it, and it relates to, QuEra's big news from December with the execution of an algorithm using 48 logical qubits. We've mentioned logical qubits, we've mentioned fault tolerance, error correction. So can you talk to us about this, the challenges in getting to this, and also, what do all of these things mean? Like, why is this important to the quantum community?
Absolutely. So let's take a moment for a motivation speech there. Notice that the computers that we have today, within the superconducting space, they operate usually with about 1% error. Depends a little bit on whose machine you're talking about, sometimes a little less. When you talk about neutral atoms and ions, we are in the 0.5 or a little less errors. So we use the word fidelity of operations. It means that these systems, they are not immune to errors induced by the environments in which they are immersed. So operations with 99.5 fidelity on, we call 2-qubit gate operations, which are the entangling operations that generate this mysterious power of entanglement that allows for quantum calculations to work. This means that out of 100 operations, 0.5 of them are actually not going to do what you wanted them to do. Now, the number of logic operations that you want to deploy in a given system to actually run an algorithm can be quite large. If I have a 0.5% error, well, within a couple hundreds, between maybe max 500 operations, you certainly have seen errors. you certainly have seen errors, right? Like if it was a 1% error in 100 calculations, you say, oh, change this 0 to 1 or rotate this qubit to whatever, you will see an error there and your calculation will go to space. Bye-bye. Now, what we need to be able to deploy these large simulations of chemistry or factoring of integers into, we here for cryptography applications, we are talking about millions of operations. So this means that that 2-qubit gate fidelity of 99.5 or 0.9, let me push, would need some 5 or 6 nines to be able to operate like 1 million times or even more. Okay, we talk about the need of even like 10 nines to be able to do calculations. We have been working a lot on improving qubits. Neutral atoms have ion traps, photonics, superconducting. Everyone is working on improving their qubits. There is no one that has any hope of getting 10 nines of precision on their operations. No one. The only way to do that is to do what's called error correction. Error correction is something that happens in classical computing and in telecommunications as well. And before error correction was invented, which came just a few years after Peter Shor's famous factoring paper, no one believed that quantum computing was going to be a possibility. The moment where quantum computing became a say, this is actually possible, was when we realized that it is possible to do error correction, which means to generate redundancy in a system in order to account, to find when mistakes happen and correct them before you continue your calculation. And the basic mindset is something like for a classical system, right? You have zeros and ones, 0, 0, 1, 0, 1, 0, 1, 1, 1, and so forth. And if you have a 0 or a 1 and you don't know, because sometimes your 0 may become a 1 during your calculation and you didn't want that to happen, what you do, well, instead of taking 1 0 and 1 1, you take 3 zeros and 3 1s. And whenever one thing flips, you do a majority vote. If it was 0, well, it became a 0, 0, 1. Majority is still 0. So you can still say, okay, this was actually a 0, a mistake happened, make that 1 into a 0 again and continue. Right? So by doing redundancy, you can kind of build confidence on what's happening on your system. The question is, the bigger you get, the more errors you could also generate. And the non-triviality is that for quantum error correction and classical error correction as well, you can get exponentially better results from larger and larger redundancy that you apply in your system. So when we talk about 48 logical qubits, that's what we have been doing. We were able, so this was an experiment led by Harvard and with help from QuEra's tech to encode information of 1 qubit into patches of more and more qubits, 7, 8, it varies the way you're doing, and verify that the larger the patches, the better is your error correction. So there were 2 different experiments, or there were multiple experiments. It was a big paper, but some of them we were doing error correction, some of them we were doing error detection. The 48 logical qubits was an error detection experiment, meaning that in the end of calculation, you are able to post-select the results for which ones are trustworthy and which ones are not. But we certainly did error correction as well. Okay. And that was a demonstration that the architecture idea for neutral atoms of moving atoms and creating what we call zoned architectures, so areas of the computer which are good for entangling, areas that are good for memory, areas that are good for measurement, that really works, right? We were able to demonstrate operations with logical qubits with a factor of 24 more than anyone had demonstrated before. Okay. So people had demonstrated 1 or 2 logical qubit operations. We have demonstrated not only the operations of 48 logical qubits, but also the composition of very complex algorithms with it. So that's what was the big move. So we're very excited about it. Again, this was a demonstration within machines from within the Harvard lab from Michel Lukin. QuEra, we are always a spin-off from Misha's lab, and we have been consistently, speeding up our capacity to translate, the technology from the labs to the community. So last time it took us a couple of years to be able to put a computer online that did the same that was possible to do in Misha's lab. That's the computer that we have right now on Amazon. Anyone can access it on Amazon Bracket. It's called Aquila.
Mm-hmm.
And we are really believing that within this year, we are going to have a machine that is going to be able to demonstrate some of the, for a customer level, being able to demonstrate what Harvard demonstrated.
Okay, that's very exciting.
So our roadmap is pushing for 10 logical qubits within this year, but it's really a very exciting time indeed. Yeah,
that's good. That's good. Are there any other exciting developments from QuEra that you wanted to share, or more about the roadmap?
Well, so the roadmap, if you have not seen, you can always access our website and see a recording of it. This was an announcement in early January. Mm-hmm. So we are looking at making machines that are able of operating order 10 logical qubits by the end of this year, 30 logical qubits end of next year, and 100 logical qubits for the year after, right? And with error rates that may be varying from the 10 to the -4 to 10 to the -5, which is exciting, right? I mean, this means that we will be hitting this order of 100 logical qubits to 10,000, 100,000, or even 1 million gates. So this is the moment where quantum computing, we will be having a very different conversation 3 years down the road. I think that's all I can say.
Okay. Let's have that conversation 3 years down the road. I'll check in with you, Pedro.
This conversation is already a lot of fun, and it's only going to get more fun.
It is. I think it's really exciting. I think there's been acceleration in a sense in terms of what QuEra and other companies have been achieving in the quantum computing space and in other technology spaces Absolutely. As well, like in computing and sensing and materials. It's a very exciting time to be a part of the quantum community.
And I want to emphasize that we learned a lot from the community of superconducting qubits and ion traps. By no means we got here by just working by ourselves. Okay, there's been a lot of lessons learned from the whole community. So kudos to everyone, and I'm pretty sure that we'll be seeing great demonstrations from all around.
Absolutely. Okay. Well, this has been great. I'd like to, to wrap up our conversation, give you a chance to talk about your blog. So if you'd like. So you recently launched a blog called Set Physics to Stun. And here you have an opportunity to tell us about it. First of all, what inspired the name? I could be wrong, but I think it's a Star Wars reference.
Star Trek.
Yes. But yes, let's hear it from you. Tell us about your blog.
Absolutely. So Set Physics to Stun is been on the works for a while for me. It took me a lot of time to develop the motivation to put the whole system and a website together to host it. But it came out from an inspiration of mine. As I mentioned, I really wanted to start contributing to enable some innovation in the space of managing science endeavors, right? So we say management and administration within not only academia but any scientific space, and people usually cover their eyes, their mouth, or their ears, right? Like they don't want to hear about it, they don't want to talk about it, and they don't want to see it. But as we scale up and as we start to see the complexity of relations between humans and the needs to create environments that are more functional and egalitarian and so on and so forth, I think that it's past time that we start discussing a little bit more seriously how we can make these scientific environments better and take care of our scientists, right? I've been one. Deep in my soul, I am one, and they deserve care because I think that it's such an important community to help advance human life in humankind. So in this vlog, I talk a lot about some of what I hear, and I try to amplify a little bit the information that I hear about managerial practices in science. Some of them I develop myself. So it's a good way to learn a little bit of, I think about this every day. So to see what I'm thinking about. Sometimes I talk a little bit about physics. I have not made a post in physics yet, but I definitely have something on the works. And the idea there is to talk about topics in physics that are kind of to set physics to stun, to get people excited about it. To it's basic physics, but that gets people really feeling, oh, okay, this was under my nose, and I didn't realize that I didn't think about it. So
yeah, absolutely.
Yeah.
Okay. Well, that's super exciting. I'm excited to see your future blog posts coming out about it, about both management and physics. I'm excited for both, as also an interdisciplinary person. Okay. Well, this has been a great conversation, Pedro. Thank you so much. It's been great having you. And yeah, it's I guess we can end it there.
Yeah, it's been a great pleasure. I hope to see you again soon and talk
Yes,
to
absolutely.
everyone. And thanks everyone for listening.
Great. Thank you.